Welcome back to Savage Fabrication Instaspool Performance, our YouTube channel on understanding all kinds of cool mechanical things. We've been talking about turbochargers and air a lot. We still have a lot to do with that, but thought we would switch it up and talk about something that nobody talks about. There's some videos on this, but not a whole lot more specific to gas engines. I don't think I've come across anything YouTube-wise that has to do with brake-specific fuel consumption ratio when it comes to diesel engines, and in that matter, performance diesel engines. There's two ways to look at brake-specific fuel consumption ratio. The normal way that if you were to Google this, it's going to show up as it looks like a compressor map with numbers all over the place, and there's a really efficient region where peak torque is going to be, and then there's a really inefficient region, and in between the really inefficient and the most efficient is where your peak horsepower is going to be. That's a little bit more intricate and doesn't really apply too much to performance diesel, more so over the road stuff when it comes to trying to get the best fuel economy. From an OEM standpoint, like if you're manufacturing the engine itself and designing all the parts and pieces, that's what you would be using. In our case, we're really just looking at the numbers themselves when it comes to making horsepower, getting distance down the pull track, putting up numbers on a dyno, and getting good time slips at the drag strip. Or just if you want to show your friends up with your diesel engine, this is important stuff to know because this will help you out. So first of all, we didn't miss a word here. Brake-specific fuel consumption ratio. I know, shots fired. So, what is it? Well, what it is how much fuel is consumed by weight. So in this case, it's going to be a pound. You can do it by minute if you divide it by 60, but we're going to use pound. So it's how much fuel by weight in pounds is burned per hour to create 1 horsepower. This number typically will be between, for diesel, it's going to be between 0.2 to 0.5. But we can get into where it goes above that, and I never calculated it below 0.2. And it usually have to do some pretty extreme things to get to anything below 0.3. So in this case, if we were to look at it this way, it would be, if we had a 0.39 brake specific, and that means we burn 0.39 of a pound of fuel an hour to create 1 horsepower. A gallon of diesel is 7 pounds. So 1 gallon equals 7 pounds of diesel. Now, all your different fuel types all weigh different. You want to look this up. If we're to say methanol, 1 gallon of methanol is 6.58. This is actually 6.98 or 6.97. 7 pounds makes it easy for doing math. So you want to look up the fuel type that you're using to figure a lot of this stuff out. But in this case, we're going to kind of stick with diesel fuel, and that's 7 pounds per 1 gallon. So we're going to continue. Kind of know what it is. Why is it important, or what makes it important? Well, there's two. Why is it not talked about maybe in gasoline or spark ignition, the gasoline spark ignition industry? The big thing that we don't see it talked about in the spark ignition industry is because it's easy to put more fuel in. When you look at like pro mods or even just street and strip type stuff, where you can just keep putting more injectors because they're port injection, you can get a lot of big injectors, and the injection timing isn't nearly as, it's super critical, but it is not as critical as direct injected because the time window is so short. Some guys that are into doing performance heads and engines for spark ignition engines go over this repeatedly, that the window of opportunity to get fuel in the chamber and mixed properly is just too short. They don't have the pressure. That's why when you look at column rail systems or even our mechanical systems, our injection pressures are extremely high when compared to the injection pressures of, say, a port injection system. And even direct injected gasoline stuff is still not to the point where it's as high as where we are at with diesel fuel. So that's a big thing, is we have to think of it from the engine's perspective of how fast the piston is coming up the bore, hitting TDC, coming back down the bore. That amount of time is extremely small. We can get a really good idea of how small it is by looking at common rail injection and how long to keep the injectors open for. US, when it comes to common rail, if you're looking at tuning, or you might hear people talk about, it made 700 horsepower at 1500 US, it made 800 horsepower at 1700 US, it made this horsepower at 2000 US. US is microseconds. So that would be 2300 microseconds, 1800 microseconds. That's how long the needle is lifted for. And on top of that, that's not a full lift duration, because it takes time to energize the system, and then the pintle has to be lifted, and that all takes time, and this is all extremely relevant to things that are happening in a world that lives in microseconds. So when we get into mechanically injected stuff that has lower injection pressures, we tend to see higher brake specific numbers. Not always, there's ways around that, but some of the ways aren't either, one, affordable, or two, street friendly. You can figure out the factory brake specific for most of your setups with an ID tag that comes on all the engines. It'll show it in a millimeters cubed. And we can go and use millimeters cubed, convert that over to cc's, and figure out the brake specific. Like a VE truck, we did one the other day, a non-intercooled VE, came out to be about a 0.43 brake specific from the factory. Common rails, they change by year, but they were like 0.39. I think P pumps were also around the 0.39 or 0.4 area brake specific from the factory. So we're going to get into still why it's really, really, really important. The two things that make it important in general is, if one, you're looking at it for fuel economy, or two, you're looking at it for horsepower. It's because, like I said, gasoline or spark ignition can just put more injectors in. We can't just put more injectors in. So we're really a fuel limited setup, as well as how our AFR works makes us also fuel limited, and the burn duration of the diesel fuel itself also poses problems when we get into performance diesel. So most of us diesel guys are fuel limited. We're pretty much, it's pretty rare that we're air limited, and if we are air limited, it's an easy change. We go to compounds, we go to bigger turbos, we raise the boost pressure, we turn the engine to a higher RPM. Air problem solved. Fuel limited tends to run into issues where we can put bigger injectors in up until the point where the injector got bigger but the pump won't push anymore. So we tend to see, like on VEs, VPs, and P700s, is there's the upper limit to how much the injection pump itself will push through even a really big injector. So it'll hit. With mechanically injected setups, we find that we tend to be injection pump limited on CC. So the injection pump is calibrated to flow a maximum number of CCs. The injector tends to always be smaller from the factory than what the injection pump maximum is. So if we say we have an injection pump that flows 400 cc's, but we're on a stock injector that flows 170, we go to a performance injector, and now we're at 300. Now we go to a higher performance injector, and we're at 400. We'll see power gains each time. Now we go to a higher performance injector, and we're at 500. But we're still going to make the same horsepower if we don't run into injector line pressure fall off. We're going to make the same horsepower as we did with the smaller sticks. And in a lot of cases, we'll actually make less horsepower than we did with the smaller sticks, because the injection pump's now having a hard time maintaining line pressure to keep pintle lift up in the system for the entire injection event. So that's the limit. And that limit, you need to know what it is. It's really, really important, and it's one of the biggest things, I guess, that we run into on the chassis dyno with the mechanical trucks, is everybody turns their injection pump up. Look at, I did it. I've done it quite a few times. I've had VEs and I've had P700s. I have turned them all up, put injectors in them, and been extremely disappointed on the dyno. And I blame the dyno for the lack of horsepower, not my own fault for not understanding how the injection system works for lack of horsepower. So you have to know these numbers. If you look at it from the spark ignition side, they know these numbers. They don't have a pump that flows 400 cc's. They just put in, if it's a 4-cylinder, they would put in 4 1000 cc injectors, or 4 80-pound injectors. They know all this data, and this data can be added up together to find out how big the lift pump needs to be, to find out how much power potential there is in fuel going in the chamber. We've had this thing going on where we don't really know that because we just go and throw a bunch of parts at the injection pumps, and then we go put them on a dyno, and because the forum said we're supposed to make a certain horsepower, we don't make the horsepower, we blame the dyno operator. It'd be nice if we can start working on understanding the injection systems better so that doesn't happen. So the big thing that we see is the stock injection pumps seem to have a limit of about 290 to 330 cc's. That's not always the case. There are special cases, and we don't want to believe in the special cases as everybody is gonna get the same thing. Like you get these power kits where it's DVs, injectors, and gov springs, and it's a 500 horsepower kit. The problem is that's not guaranteed to make 500 horsepower if the injection pump only flows enough fuel to push through the injector 400 horsepower, and then you're mad at the dyno guy. So we're going to look at why this is, so that's why it's really important, because we have this really small window of opportunity to put fuel in. We also have limited quantities of fuel. The next thing is diesel fuels, brake specific, unlike any other fuel type, has, that I've studied, should put that in there, that I've studied and looked into. It has the widest brake specific margin out of all the performance fuels that we've looked at. So like if you look at methanol, you look at gasoline, they have these brake specifics that are they can be a little bit wide. They can be 0.4 to 0.7 type of deal, but it's not too big of a deal because you can just add more injector in. But diesel, we can be say 0.2 to 1.5. We could run as lean as you possibly can. You can say the 0.001 and the engine will die. You could also run rich until the engine shuts off, or you start doing cylinder wall damage by too much fuel in the chamber. One of those two things will happen. So we have this really wide brake specific that we could run in from say 0.3 to 1.0, where the motor will run fairly all right. This is probably going to be pretty dirty. So cleanliness wise, 0.3 to about 5.65. This still might be a little bit dirty, but the engine will run and sound like it's making power even running this high. So we're going to go into why these numbers are important. And the cool thing with diesel though is if you do all this stuff and you find out that you are up here, this generally means if you have all quality components that all you need is tuning. And you could tune this thing down through timing and how we bring the fuel in to get us down to a 0.4, 0.35. You're probably not going to see a 0.3 without really, really high boost pressures, a really big injection pump, or nitrous. We're probably going to see a base minimum of 0.35 is going to be, generally speaking, oops, that's bad. Almost got to stand here. Absolute. If you can get to here, that's awesome. The thing's going to run extremely clean. EGTs are going to be sub 1500 degrees at realistically any kind of horsepower you want to be at. Fuel only, so this is fuel only. When we put nitrous in the mix, this number will continue to drop down. But the next thing is we'll go over why on limited fuel, like our diesel engines where you mechanically injected, say we only have 390 cc's, or we only have 300 cc's, or we only have 600 cc's, that's all we got. How do we make the best of it? How do we make the most horsepower? Because we can't just go turn the injection pump up. We've already had our injection pump built, it came back, benched and flowed at 600 cc's, and we're not making 600 cc's worth of power. You can stick with your low horsepower setup and get your butt whooped by everybody that spent the time doing proper tuning, or because you're going to blame dyno operator for low horsepower, yet you're still not going to win the races. Or we can go and do some tuning and make this thing run better. A lot of that times too is just cheap injectors. Cheap injectors are like the bane of pumping this number really high. Cheap injectors, not enough timing will make this number really high. And the higher this number gets, the more fuel it's going to take to make the same amount of horsepower. So let's take 600 cc's. Let's say we got a pretty nice pump. We have 600 cc's worth of fuel. We're going to find out why the brake specific is really important. So we're going to use 600 cc's. MM3, we need a flow sheet of the injectors. I have pictures of them. But we can do a video on understanding the mm cubed. That's what it is. I just call it MM3. But MM cubed, millimeters cubed, is how all of the common rail systems rate the injectors. And the millimeters cubed is going to be is going to have different numbers based on the US, or the amount of time the injector is left open. So we can kind of do a different video on how to understand what that is, and how to interpret it, and how to convert it to cc's. Whatever reason the diesel industry operates in millimeters cubed, when all the other industries operate in cc's and pounds. So we're going to have 600 cc's. In this case, we're dealing with a 6-cylinder engine. So it's going to be 600 cc's times 6, because we have 6 injectors. So 600 times 6 is going to come out to be, yeah, it's my car hole, 3,600 cc's min. So now we need to convert this over to pounds hour. I have a website that will link that you can go use to do this. 3,600 cc's a minute converts over to 342.9 pounds hour. So that's what we got. We don't get more than that, and if our foot isn't wide open throttle, then we get less than that. So the next thing that we're going to do is we're going to show you why brake specific is so important. So at 342.91 pounds fuel moved hour, we will take that number, 42, 1, and divide it by our brake specific. So let's say we're going to do 0.65. So this times 0.65, so very poorly tuned setup, or sorry, divided by. Is going to yield 527.5 wheel horsepower. We do all of our brake specific stuff based off of wheel horsepower. You can do it off of crank horsepower, but you need a engine dyno. We do everything on a chassis dyno, so all of our math is based off of what will match up with what we see on the chassis dyno, because that's the most helpful way to use the tool. Is we base all of the equations off of what we either one, expect to see, or what we have seen, and now we are breaking it down to try and find where the issue is. So let's say we did some tuning. Let's say we put 5 degrees of timing in. Let's just say the thing was at 20 degrees of timing, and we put 5 degrees of timing in, and that dropped us down to a 0.48. So we divide again by 0.48. So go back in. 342.91 divided by 0.48. So without changing anything other than making the combustion event more efficient, because the fuel put in is the same. We had the same BTUs, or heat energy, or just total energy, however you want it, heat energy, total energy, same total energy put into the chamber. We just made it, the working effort, more efficient on the piston, because we changed where the burn was occurring and ending based on crankshaft position. So by making it more efficient, our brake specific went down. We're still putting 600 cc's in with 6 cylinders. We now made 714.39 wheel horsepower. So basically just went up 200 horsepower by just adjusting timing and doing some tuning. And that's the crazy thing with diesel fuel is this is real and this happens a lot. The biggest thing that we see, it's not as common in common rail stuff. I think a lot of the bad tunes or bad tuners are going away. Maybe I'm wrong. We try and send everybody to people we trust as far as common rail tuning goes, but for the most part, a lot of them do okay. They tend to be in the 70% range of, for the most part, being pretty good. The worst offenders of this are P700 guys, because it's so easy for anybody to throw parts on them. And we're not saying to not do it. The big problem that we have is that you get the internet or these shops, businesses, claiming that this is a kit for this much horsepower. And that is really, really hard to do with an injection pump that has 100,000 miles on it. It has 200,000 miles on it. It has 400,000 miles on it. And we do not know how many cc's the injection pump moves. Putting bigger injectors in the engine does not make the injection pump move more cc's. Putting bigger DVs in does, but you got to be careful because you also increase the duration when you put delivery valves in a P700. Duration is not too helpful in making horsepower. We tend to see whenever we increase the duration, we do increase the cc's, but we tend to hurt the brake specific. So in this case, we would want to put in more cc's than what we lost in brake specific to see a gain in horsepower. Also, when the brake specific goes up, things tend to get dirtier. When the brake specific goes up, things tend to get hotter. So those are really key ways to look at a setup. 0.45, it'll be probably hazing at 0.45. 0.5 is going to be dirty. 0.6 is going to be dirty. We're putting a lot of fuel in, but not getting a lot of return from the fuel. So, and this is important too, because all of this, the air, for as much as we talk about turbochargers, the air is not the horsepower. The fuel is the horsepower. The air is kind of like a catalyst. It's a mixing agent that has to go in there to allow the fuel to burn so we can extract the BTU energy from the fuel and turn it into horsepower. So this is a 0.48, so 600 cc's. We can go to like the extreme. Say you've got everything dialed, you've been working on this thing for a year or two, you've been doing pass after pass or pull after pull or dyno run after dyno run, making small adjustments. Everything's good. All your components are of a quality manufacturer. You have your data. You know it's 600 cc's here. You had a good injector builder that knows his injectors. You have either on several different dynos in different locations made the horsepower it's going to make, as far as them getting their own data, or has essentially like backup with time slips and flow patterns and all that crazy stuff that they're fully capable of flowing the amount of fuel that they need to flow for it to make the horsepower. So we had everything dialed in, did a 0.35 with 600 cc's. 2.91 divided by 0.35. We had a potential to see 979.74 wheel horsepower on 600 cc's. So the fuel type did not change. The only thing that we did change was basically how much fuel was put in. So how much BTUs or loud bird. How much of the work energy in the fuel was actually turned into work on the crankshaft. So that's a really neat thing that diesel fuel can do. And it can be all over the place. It tends to always run higher when you do all your new parts. So you throw your new injectors in, or you throw your new DVs in, or you put your new injection pump on that flows 600 cc's. Putting all the parts in at one time rarely nets you the peak number the first time out of the gate. We get this a lot with mechanical and common rails, where they go put big injectors in, or they'll go put a big turbo on, or they'll go run dual CP3s, and have it remote tuned, or in the mechanical case, they just put all these things in there, and the first run out of the bat, it's supposed to do what the internet said. Makes a lot of people frustrated. We've seen a lot of not an angry customer, but they're just kind of upset that the thing didn't make the horsepower that it wanted. As far as after they used our dyno to run on it, and the horsepower number was lower than it was. So the big thing with understanding this stuff, though, is we can tell the customer that, look, if you can give me all the information of the injection system, we can go and run all these numbers and get pretty close to where you're at. So then we can go make an educated decision on what we should change to decrease the brake specific, so we can make gains in horsepower and reduce smoke output, gain in horsepower, gain in torque. Just everything gets better after we do some tuning. So I think I've explained brake specific pretty good. I hope it makes sense. But you have to know these numbers. If you don't know these numbers, then you have to run on a dyno and take video in cab and video outside of the exhaust. We need video outside of the exhaust. We need gauge data, and we're going to need a dynograph. From those things, we can start looking at getting pretty close to what the injection pump or system's currently moving. Because we can look at smoke opacity, we can look at horsepower output and that stuff to get a really good idea of what's going on. So the trucks, like say the mechanical stuff, the stuff that we mainly deal with, they are getting older, like quite a few videos from other people have said, and then some of them come with mismatched parts, or the parts are getting worn. So it's getting more common for us to actually know the flow rate of the pump because they've been replaced or they've been benched and flowed. So that's really important. We don't really need to know what the injector size is. The injector is like the most important thing, but we don't really need to know its flow rate because we don't build injectors. We try to stay away from recommending injector size. What we do is we get the pump built for the horsepower we want to make, and then we call our injector builder and we tell them this is what we have. We need an injector to do this, and we entrust the injector builder to know what they're doing and to get us a quality set of injectors, so we can then go do our part with the tuning. We're not really here to tell the injector builder what injector we want. That's their job, not ours. Same with the injection pump. We just tell them the horsepower that we want to do, when we want to do it, and all that fun stuff. And then they tell us, hey, it's going to cost you this much money. And you're good to go.
No, this is more of a thing. Is because you say it's called US?
Yeah.
Which I assume is just how people are using it, because the U is actually the symbol for micro.
Yeah, it is the symbol.
So it's not actually US like United States. It's just the symbol for micro looks like a U.
Yeah, but everybody says US.
Yeah.
If you're watching even anybody's dyno videos, they're like, it made 700. They'll say U. Everybody that's just a standard. That's what it is. Just like BorgWarner turbos have names, but BorgWarner sees them as part numbers. The only reason they have names is so we can communicate to each other about what turbos we have. But if you call it BorgWarner, they're gonna want to know a part number, not a S362. They want the part number off of it so they can help you.
It's S362 BorgWarner. Come on, you make it.
Same with you. Like the US is just so we can communicate with each other.
So this question might go into your duration thing, but like, what goes into determining your? Well, you said in the beginning like 0.2 to 1.2 or whatever.
So what makes it that?
Yeah, like what in the fuel is determining whether you're getting that like 0.39, 0.65?
Well, the fuel type sets like what it can be.
So the fuel is your band.
Yes. Like gasoline, 0.4 to 0.7. 0.7 is forced induction, 0.4.
So it's like a narrow band.
Yeah. Like if you try to run 0.4 on a forced induction gasoline engine, it's gonna lean out and die. Like, yeah, You have to run in that. You have to run in these set margins for the engine to survive. But it's not really too big of a deal because it's easy to put a lot of fuel in. And it doesn't make black smoke when you run an AFR. It's a little bit lower than normal, so they don't get called out for black smoke. Where our diesel fuel creates a bad acetylene burn in the rich zones in the chamber when it runs a low AFR, and we get soot where gasoline doesn't do that. So we get called out for soot when we try and get down into the horsepower areas of the AFR curve, so we gotta run this really high AFR.
So you're saying low AFR would be a higher number. You're saying low AFRs make more smoke.
It depends. That is a semi-tricky thing because the duration of the injection event, you can have a low AFR with diesel fuel, but with a really fast injection duration, a really fast injection duration, and a really fast burn rate of the fuel. So you've modified the burn rate by mixing in methanol or a lot of boost pressure.
What about like cetane?
Cetane's... It's been a little bit since I looked into it. Cetane makes it burn faster. You can do that. Yes, yeah, you can't. The polars do it for to get the burn faster because that's diesel's like diesel fuel's enemy is that it burns really, really slowly, where gasoline burns very, very quickly. So you don't have that much. Usually, like gasoline engines with forced induction, you're trying to slow flame speed down. You're trying to keep it subsonic. Where diesel fuel, we're trying to get the flame speed up because the piston's moving extremely fast through the cycle, and there's a really narrow window to put pressure on the piston to make power, and anything after that is basically a high brake specific because it's inefficient. Basically, the pressure front is chasing the piston, so the amount of pressure on the piston head is greatly reduced versus if you could have got your main pressure duration to be up in this higher area. You would have put more force on the piston if you would have started and completed the burn in this window than if you complete the burn in this window. So if 600 cc's burns this long, then you had like this much time before you pushed on it, then the pressure front's chasing the top of the piston down, not doing a lot of work effort. It's creating torque, but it's not really creating horsepower. Where if you did it all up here. Gasoline, you're trying to keep it subsonic so you don't knock or blow the, what's it called? Basically blow the air cushion off the cylinder wall and stuff goes haywire. Basically, if your flame speed starts to go sonic, it creates enough heat at the face of the pressure wave to just ignite stuff without a spark. And it also knocks this air cushion off the cylinder walls, which will cause damage.
So if an AFR of like 0.35,
well, no, AFR is going to be...
not AFR, sorry, your brake specific fuel ratio.
Yeah.
Right, so we're at 0.35, 0.40, whatever. Like the lower it goes, right, the more power you're going to make.
Yes.
And the less smoke.
Mm-hmm. Yep.
So why does every high performance competition diesel blow smoke all over the place? Wouldn't they want no smoke and to have a lower brake specific fuel ratio consumption? What are they gaining by having the smoke? Like, is it they are so far beyond they're making more power with a higher brake specific fuel consumption ratio than they would if they lowered it down?
Yes. That and yeah, if you're looking at like competition setups, well, and one, they don't have any fuel modifiers in them. They have to run a spec fuel that has no oxidizers in it. Some allow you to get away with B100, which has oxidizers built in, which is really cool. Which would have a, okay, so yeah. Well, I mean, yeah. They have like unlimited, I shouldn't say they have unlimited budgets, but they have a lot of money to spend. So they're running, say, a 16 millimeter pump or a 17 millimeter pump that can put out 1800 cc's a fuel, they would rather put in the 1800 cc's with a lower brake specific, and you're probably going to end up with a low brake specific just because it's direct injected, and still make more power than if they were to try and get it to burn faster. But what happens when those big 16 mil pumps, their duration gets really short. Like if you try to do 1200 cc's with a 12 mil, you'd have a really long injection event. So the piston would be like way down the bore by the time you got 1200 cc's in, making it null. So you got to make the plunger larger, so it pushes more per millimeter of lift on the plunger head, which means more goes out the injector on the opposite side. But there's still a limit to that. You can only have such an extreme ramp rate on the camshaft inside the injection pump. So yeah, I'd say that's a fair statement. It would be a trade-off. I mean, the same thing happens with methanol. You put methanol in, and methanol runs like a 1.5, like methanol fuel in a race engine. It has like a 1.5 brake specific. But because it has an oxidizing agent, it holds oxygen inside its chain, it takes less air, and it's easy to put more methanol in. So I'd rather run this high brake specific, put a lot of it in, and make a bunch of horsepower, than try and do the same thing on gasoline, which would not be possible to do. There's a limit to how much you could put in there before it just doesn't, either one doesn't work or blows up every time. Yeah, I've never really, because their stuff's so kind of top secret, it's really hard to kind of do math equations with their stuff. Once you get past, for whatever reason, Probon stuff seems to not be that secret when it comes to the spark ignition world. You know, there's books and everything, but the diesel industry is still pretty top secret on a lot of stuff. So it gets hard to do kind of guesswork. One of the things that I've kind of gotten to do is some of the local, not local shops, but more talkative shops that do have big injection pumps, but never run them at their full travel, will do runs. They're like, we got this 16 mil pulled back to 600 cc's and it made this much horsepower. I'm like, perfect. You said it in a video, I can go do my math. But they've never done, they've never put it at full rack or full, fuel plate full forward, made a run, and then disclose what they made. There's some close things, or they don't tell you how many cc's it's doing at max. So it's really hard to even kind of figure out what's going on with that stuff, just because it's so top secret. to some, you know, I don't see, it'd be real helpful. We get to learn a lot if we had that information, but we don't. Super secret sauce. But you know, you can do all this stuff with the lower things. You know, there seems to be a crossover point about 120 pounds of boost. The brake specific starts to get lower, and that more than likely has to do with the amount of oxygen content and pressure in the chamber is actually starting to speed up the flame speed a significant amount. So we start to see a brake specific drop at about 120 pounds of boost. Injection duration's getting shorter while more fuel is getting put in. So 13 millimeter pump, 14 millimeter pump, 16 millimeter pump, or you know, CP3s with really big injectors but then really low US tends to lower brake specific, which is always a good thing because there's less duration but the same quantity of fuel going in, if not more. And nitrous lowers brake specific because the common idea of seeing nitrous is that it adds oxygen to the burn and cools the incoming charge. All 100% true. The one thing that nobody talks about is that when you add a high oxygen content to a mixture, the flame speed goes up drastically. And that is where a lot of the horsepower from nitrous is coming from, is the flame speed going, especially with diesel fuel, with its really, you take something that burns really slow and then you make it burn really fast, so it's really easy to put that full amount of fuel, the burn window, in the most optimum window, and the power just goes up like crazy. So like nitrous, really big injection pumps, or a lot of boost pressure are the only things that we've really seen with the, you know, let's say a 5.9 liter and up engine. At the tire, bring the brake specific below 0.35. And it can actually drop it down to 0.22 to 0.24, depending on how optimized the system is. So that probably wraps up brake specific. It's pretty easy. But if you have to know your, you need to know the amount of fuel you are moving or putting in the chamber. And it tends to be based off of maximum. If you have a system where you know the different throttle points, you could also do the same thing and calculate at the different throttle points if you want, but typically we're just looking at calculating the maximum amount that we may see. So in the case of the older mechanical stuff, we all use cc's. So if I know I have an injection pump that flows 420 cc's, if I know I have an injection pump that flows 800 cc's, or if I have an injection pump that flows 320 cc's, yada yada yada, it's the pump's cc's multiplied by 6 because we have 6 cylinders. You're going to convert it to pounds-hour. You're going to take your pounds-hour and divide it by your brake-specific fuel consumption ratios. These are going to, and if you never ran on a dyno before, what I like to do is do an array. So do a 0.65, 0.6, or you do a 0.6, a 0.5, a 0.4, and like a 0.35. More than likely you're not going to have a 0.35, but it doesn't hurt if you want to see what could happen if you spend a lot of time doing the tuning. And that gives you a good idea of what we're probably going to see in the dyno. The other thing is, I don't know if I can talk about this right now or not, but it seems to be consistent on the chassis dyno that we're missing cc's. And I think we didn't take into account injector leak by. So common rails do this. Common rails take into account how much fluid leaks by the injector parts for lubrication, as well as just how they are. And there's a tolerance, plus or minus what the tolerance is. I've looked into that, and then I've taken what I seem to be missing on the dyno on mechanical trucks and taken that away from the injector, say take that away from the same injection pump. So if the pump flows 390 cc's, then I'm missing 90 cc's. And I take that out and then I do my math. I actually seem to net much better numbers than, like more accurate numbers than calculating the full pump cc number. And I think that's kind of important because the injectors, the return line on our injectors is designed to return fuel that has leaked by the injector or is being used as lubrication for the injector. It is not fuel that was not injected into the, it's not a return for excess fuel, I should say. So the fuel return line on our diesels is not a return line for excess diesel fuel not injected. It's a return line for diesel that was used to lubricate the injector and to just leak by that could occur internally of those components. So, and this would change. Say the leak by, say 90 cc's at 3,000 RPMs, the number would go up at 4,000 RPMs, the number would go down at 2,000 RPMs. So we do this at 3,000 RPMs. At 3,000 RPMs, it seemed to be very consistent that we are missing 90 cc's. So like on our chassis dyno, if my fuel pump, injection pump flows 390 cc's, then I'll go 390 minus 90 times 6, convert, and then do my math. And then we'll get over on the dyno, and we're actually pretty dead nuts with what we want to be. We can use the truck that I drive every day, 390 cc's minus the 90, do all the math. It actually runs a 0.43 brake-specific fuel consumption ratio at 398 wheel horsepower that we drive every day. So,
wow, not even 400.
I'm gonna ghetto fog it. So that seems to be consistent. We had a mechanical truck a few months ago, kind of do the same thing, 600 cc's. It was a 0.65 brake specific for the horsepower it made, which is kind of, I mean, that's fairly not common. That is really high. So I just took 600 minus the 90, then did the math on that, brought his brake specific over to like a 0.58, which probably feels a little bit more realistic. And then from there, told him we can go from 0.58, we can do timing and tuning changes to get us down into the 0.4 area. 0.4 is usually where you want to try and shoot for. That's pretty realistic as far as trying to get everything dialed in. It'll be a clean burn, it'll be a cool burn. It'll probably have a haze under wide open throttle, but the EGT should not be out of control while operating below the peak torque range, and then should be between 12 and 1500 between peak torque and peak horsepower. But that's something that we've noticed on our chassis dyno, that we just seem to be missing CCs, and I just kind of would do the math without thinking about it, but I'm like, I got to figure out where this is going. And I started looking into what's okay for column rails, and they actually have more than 90 cc's leak by on a column rail injector. So we actually, on the 12 valve in this case, for the 12 valve we have less leak by than a column rail does. So it seems even more realistic that to say missing 90 cc's at 3,000 RPMs is a valid statement to make. So just take that into account when you are running on different people's dynos. Some dynos read high, some read low. You want to run on the same one over and over and over if you want to actually start learning what's going on. Don't change dynos or chase dynos until your setup is dialed on a dyno, and then go chase different ones. Have fun. But don't make a change. Don't do a dyno run, make a change, and then go do a dyno run on a different dyno. You literally don't learn anything every time. You're not going to learn nothing from doing that, because the calibrations and locations and all that stuff are all going to be different. So it's real hard. Chassis dynos are a tool. Like I said, they're a tool in this case for making this number better, so we can make more horsepower with a fixed amount of fuel, because we can't put more in. All we have is that amount. That's all we can put in. We noticed that it's not making the horsepower we want because we did the math and saw what the potential could be. So then we go back and we start making changes to try and get as close to that as possible. Based on the system, based on the amount of boost pressure, based on the compression ratio, based on the RPM, based on the conditions outside, based on the intercooling, based off of if there's any fuel modifiers going on. We try to get the number to be as good as it can. So on that note, please remember to like, subscribe, and comment, because diesel is cool. This is Savage Fabrication, InstaSpool Performance. Y'all have a good day. Let us know what you want to do next. Maybe we'll go over, since I did this one instead of the compounds, maybe next time we'll go over how to actually calculate compound turbochargers, because there's a few equations missing from a lot of the equations that are out there that'll help make sense of why a system is either one, making the horsepower that it is and you think it should be more, when in all reality it might be making exactly what it's supposed to. Or if you're looking at how to pick the right chargers for your setup, we can help with that. So you can start doing the math and figuring out where you want to be. So thank you for watching. Everybody have a good day.